Hello all, welcome to my course on methods of addition measurement theory and practice, and today we are on lecture 19 and we are talking about the concepts of surface science and interfacial science, and we just presented one example in the last lecture. So, we derived this expression for the interfacial the interaction energy between two materials 1 and 2 which are immersed in a third medium or material, that is 3, and from this expression we showed that when this gamma 3 LW is greater than 1 and gamma 3 LW is gamma 2 LW, okay, and this quantity is positive, so this quantity is negative. So, that means in both the cases delta F 132 LW, that is negative, okay. Then we have attraction between the materials 1 and 2 in medium 3. So, what will happen is that material will go and migrate to meet material 1, something like that. And so, we presented this practical example, okay, from an experimental observation and analyze these results. So, we will continue today this discussion, and let us say now that when delta F 132 LW becomes positive. So, when this becomes positive, then these materials then the interaction energy, then the energy increases. So, that means the attraction, okay, is not the spontaneous process. So, the spontaneous process will be repulsion between the molecules materials 1 and 2 both immersed in medium 3. So, when that happens, that will happen when let us say gamma 1 LW, okay, that is let us say smaller than gamma 3 LW, but gamma 2 LW is larger than gamma 3 LW, or the opposite. So, that is gamma 1 LW is larger than gamma 3 LW and gamma 2 LW is smaller than gamma 3 LW. When either of these two conditions are met, then this delta F 132 LW, that will become positive, right. So, when that becomes positive, so then that means that these two materials cannot come together in the material 3 in the medium 3. So, let us take an example. So, let us say this is from our everyday observation. For example, let us say we have got this cooking oil which has got the Lewis van der Waals component of a dispersive component of surface energy, that is 30 millijoule per meter square, and then let us say we have got Teflon, okay, 19 millijoule per meter square, and water 21.8 millijoule per meter square, okay. So, these are values from literature. We will see that this gamma 1 LW 30 is greater than 21.8 here, on the other hand 21.8 is greater than 19 over here. So, this condition is satisfied, and we know that this cooking oil that is repelled by the Teflon. So, that is why in the cooking wares, in our non-stick cookwares, we have this Teflon coating and the oil does not go and stick to the surface. So, that is an advantage. So, that works because of this kind of surface energy. So, is kind of Lewis van der Waals component of their surface energy. Because of this, okay, this condition satisfied, and we see. So, this is one of example from practical observations. Similarly, let us say that there is an oil in oil emulsion, okay. So, silicone oil and vegetable oil, they do not mix with each other, they have very different interfacial energies. So, let us say this gamma 2, the vegetable oil, has a higher interfacial energy, that is 30, and gamma 1, that is the silicone oil. So, silicone has a lower interfacial energy. So, since it is a lower interfacial energy, that will tend to be outside, and vegetable oil having 30, it will be inside, something like this. And now, let us say that we are attempting to stabilize this emulsion, okay, by using functionalized SiO2 particles. So, these are microparticles, microspheres, and this can be functionalized in the sense that let us say this is the SiO2 particle, and you can attach molecules of different types. So, some of the molecules that you can attach will have, let us say, OH groups. Okay. So, having OH groups will allow them to interact, okay, in a certain way. Let us say they become hydrophilic because OH groups are there. So, they can form hydrogen bond with water and therefore water molecules. So, therefore, they will become hydrophilic. On the other hand, let us say that you can also attach on these SiO2 groups some other kind of molecule. These are hydrophobic molecules. So, for example, let us say there are some molecules having CH2 groups, lots of CH2 groups. Okay, these are all, let us say, CH2 groups and like that. So, they do not have any functional group that can interact with water, so they repel water. So, these are hydrophobic silica particles. So, depending on the kind of molecules which are attached on their surfaces, let us say that they have got different kind of interaction in kind of surface energy. So, this is the Lipschitz van der Waals component of their surface energy here. So, this is, let us say, 12 millijoule per meter square, and let us say this is 25 millijoule per meter square, or like that. Okay. So, now what will happen? So, when we have, let us say, hydrophilic molecules, so then delta F132, so it is delta F132 Lw is equal to minus, this is 2 here, and this is square root of gamma 3 Lw. So, 3 Lw, so 3 is, let us say, hydrophilic. So, this is for hydrophilic, yeah, 12. So, this is 12 minus square gamma 1. So, gamma 1 is 20 here, and into, let us say here, this is gamma 3, this is square root, this is 12 here, minus gamma 2. So, gamma 2 is 30 here. So, square root of gamma 2, so this is 30 here, millijoule per meter square, millijoule per meter square, like this. Now, you can calculate, this will be, I think, will be minus 4, about close to minus 4 here, yeah, this will be minus 4 here. So, that means what? That these two, so this interaction energy between this vegetable oil and silicon oil, okay, when they are stabilized by these SiO2 particles which are hydrophilic, this energy comes out to be negative. So, what it means that these particular SiO2 particles, okay, they will not be able to stabilize this emulsion. So, this silicon oil come onto the vegetable oil, okay. So, they will this or vegetable oil, yeah, it will not get stabilized, they will not be able to stabilize. So, yeah, this is negative over here. On the other hand, if let us say this is hydrophobic silica particles, then okay, this term comes out to be 0.5. You put here for hydrophobic silica particle, this is 25 millijoule per meter square, this is minus 30. So, putting these numbers, square root of 25 minus square root of 30 here, and square root of 25 minus square root of 20 here. So, putting these numbers, you get 0.5 here. So, that is repelling. So, in this case, this particular emulsion will be stabilized. Now, in vacuum, let us say there are two materials 1 and 2. So, in vacuum, so therefore, gamma 3 Lw is 0 here and gamma 3 Lw is 0 here. So, this delta F132 Lw, so that is the interaction energy between these two materials in 1 and 2 in vacuum. So, that comes out to be negative, minus 2. So, this term is always negative, and so therefore, two dissimilar materials, two different materials, okay, will always will attract each other, will okay, attract each other in vacuum, attract each other in vacuum. And let us say that this immersed in a material between two identical molecules of particles. So, identical, so that means gamma 1 and gamma 2 are same. So, if that is the case, then it is minus 2 here, and this is square root of gamma 3 Lw minus gamma 1 Lw square root, and this is square. So, this is square, so negative. So, therefore, okay, two material identical molecules or particles, okay, immersed in a liquid will also be always attractive. So, that is also there attractive, except when gamma 1 and gamma 3 are same, because in that case it will be 0. So, they will be neither attractive nor repulsive or something like that. Now, let us come back to this particular calculation of interfacial energy. Remember, we are considering only the Lifshitz van der Waals component, okay, dispersive component, and let us say water has this quantity 21.8 millijoule per meter square, and for pentadecane this quantity is 27, and for this particular rubber that we are talking about, it has this LW component of interfacial surface energy as 22.1. So now what is the interfacial energy, okay, between the water and rubber? So that is gamma 1 LW plus gamma 2 LW minus 2 gamma square root of gamma 1 LW gamma 2 LW, like that. So now this interfacial comes out to be 0.001, and for PD rubber, this is pentadecane, okay, that is an oil on rubber, that comes out to be 0.255 millijoule per meter square. So you can see that the interfacial energy is much smaller with respect to this. So if the interfacial energy is small, the energy decreases, okay, to 0, or let us say it is very small. Then in that case, this water on this rubber surface should have it spread more, because the here for this case water rubber interaction, okay, the interfacial energy is smaller than this, but the opposite case have been observed. So therefore this something is missing, okay, in this calculation here. Let us say that what is the surface tension of surface energy of water. So I will come to that point later, that how we come there, but let us say this is 72.8 millijoule per meter square, okay, and surface energy of pentadecane is remains as same as LW component, that is 27.1, and I take rubber is 23.6, again it is almost same as 23.6. So if I do not worry about the Lifshitz van der Waals component, if I just take the whole, the actual value of surface energy, the water has the surface energy of pure water will have 72.8, okay, its Lifshitz van der Waals component is 21.8, but otherwise is 72.8. If that is the case, then what will be the water rubber interaction? Let us see that. So then it will be 72.8 plus this is rubber 23.6 minus 2 square root of 72.8 into 23.6, and here it will be, this is pentadecane rubber, so pentadecane is 27.1 plus this is 23.6 minus 2 square root of this is 27.1 into 23.6, this many millijoule per meter square. So if we calculate, if we estimate by calculator, so this value comes out to be 13.5 millijoule per meter square, and this comes out to be 0.12 millijoule per meter square. So what means that if I consider the value of surface energy of water that I can measure, and how do I measure, I will talk to you later about it, I then can get a value of this interfacial energy to be 13.5 here and 0.12 here. So you see this energy is actually larger than this energy. So that makes little more sense, because water, if the interfacial energy is higher, then it is indeed should not, or it should spread less than that of pentadecane, and that we see. So water, if you dispense this water drop on this rubber surface, this has spread only this much, but pentadecane has spread this much, okay. So what it means is that the interfacial energy here must be lower than the interfacial energy here, that is very clear, and this calculation indeed shows that. So what it means is that if I consider only the Lifshitz van der Waals component in estimating the interfacial energies, and particularly when a polar molecule like that water is involved, then it may not be the right idea to consider only that LW component. We have to consider the actual value or the total, which we call the total value of the surface tension energy, okay. But this is now how correct is these values, we will like to know that. So how do I do it? So you consider this. So I will come to that once again, what is known as this Young's equation. So Young's equation will be given here as gamma, let us say rubber, which will be equal to gamma water cos theta plus gamma water rubber interfacial energy. So see here we have got this drop, and we can draw this tangent to this particular water drop, and this drop tangent makes this particular angle. So remember, you have dispensed particular drop, this drop first spreads to some extent and then comes to some constant value. So, constant amount of spreading, after that it is not going to spread. So, this is the equilibrium, and since it was spreading during advancing, so we call it this particular angle theta here, okay, as the advancing equilibrium contact angle, advancing equilibrium contact angle, that is what we call it. So, that means that there is also a receding equilibrium contact angle. I will not talk about it right now, but let us say we are happy with this advanced equilibrium contact angle, and this angle comes out to be 101.6 here, and here you measure it 32. So, that you can measure by putting this tangent and then you may finding out what is the angle. So, now here this interfacial energy between water and rubber came out to be 13.5, okay, and here it came out to be 0.12. Now, this whatever be the interfacial energies or surface energies, okay, we will come to that, we will show you that this equation has to be satisfied, okay. If that is the case, then if I know the surface of gamma rubber and gamma water and this particular angle theta, I can actually estimate or measure this gamma water rubber. So, let us do that. So, that means I have to put the numbers. So, let us say it is 72.8 and then cos of this is 101.6 here, plus this is gamma rubber. So, gamma rubber is 23.6 and this is gamma water rubber, this is the interfacial energy between water and rubber. So, this value we can calculate and this value will come out to be 38.24. So, where is 38 and where is 13.5, and if I do the same exercise between for this case pentadecane and rubber, so I will get about 0.6 millijoule per meter square, that is also even higher than 0.12. So, you see that although this value of this value that I calculated by taking the value of 72.8 and 72.8 here, so that means the total in surface energy that I took and calculated, that actually does not satisfy this equation. I mean that according to this equation this value should be like this 38.24 where it is 13.5. So, what it means that this estimation that I did, something is missing here too, okay. So, this is not also completely correct. So, that means something is missing there, and so therefore, it brings us to this idea that surface energy, okay, consists of several components. It is not just the LW or the dispersion interaction or dispersive component, it has got, okay, this is this apolar interaction, that is the Lipschitz van der Waals component, and then there are other components like this polar interaction, then this hydrogen bond and etc., acid base interaction, okay, where electron acceptance and electron donor. So, these are different interactions, and so determining experimentally the separate contribution of each component of the polar interaction to the surface tension is not easy, it is not easy. So, therefore, what has been done or what people have thought about is that we have considered this all these components, this polar, hydrogen all into one basket, that is gamma IP here, and so now the total interfacial energy or total surface energy therefore is gamma I LW plus gamma IP. Now, gamma I LW and gamma AD, okay, both are used in the literature, and in my class also lectures also some point of time I will possibly use D also here. D means dispersion and LW means Lipschitz van der Waals, so both are same here. So, when we describe the surface tension or surface energy, we have to remember there are actually at least two different components. One is this apolar Lipschitz van der Waals component, and then there is this polar component, okay. And when we estimate, we need to estimate both the things components together, then only we will have the total surface energy of a species or material. And so, you will see that this is the way it is described. So, let us say heptane, it is 21.14 and it is 0 here. So, that means heptane has only got CH2 groups, it does not have polar group. So, no polarity there. So, therefore, this polar component of the surface energy is 0 for all these cases, alkanes, heptane, octane, decane and all these cases it does not have that, including diiodomethane, okay, it has the polar component is 0. It only has the Lipschitz van der Waals component On the other hand, ethylene glycol, it has got the wedge groups, so therefore it has some amount of polar component, and so therefore it has this, and when you find out the total, it is this plus this, right. So water has got 21.8 Lipschitz van der Waals component, and the polar component is quite strong. This is 51 millijoule per meter square. So these are all actually in millijoule per meter square, by the way, okay, millijoule per meter square, all these values. So water has got 72.8, okay, that consists of 21.8 Lipschitz van der Waals and polar component 51. Glycerol has 34 and 30, like that. So that is the way it is to be expressed or understood. So now if I consider this polar component also, then my calculation, the equation changes slightly, and we write it something like this here. Actually I have not written, but let me write it here, the formula. So this will be gamma water rubber, that will be equal to, let us say, gamma water total, gamma rubber total, minus, this is 2 into square root of, there will be gamma water Lipschitz van der Waals component, LW component, gamma rubber LW component, plus gamma water polar component into gamma rubber polar component. That is the way it is. So you write this way. So now we have separately considering the interaction between the polar components of these two materials and the dispersive component of these two materials, and then adding up. So this is the mixing rule that we have developed. We are actually using that mixing rule, okay, individually for these two different interactions. And when you do that, okay, these values come out to be here 35 over here and 1.676 millijoule per meter square. And now you know that we have got, you know, the angles we have measured manually and like that. There is little change in angle, little change in the values also, but then what it shows is that 35 and 38, okay, that we had obtained earlier from this Young's equation 38, so that match quite nicely. So that's what I wanted to show you, that it is imperative to consider both this dispersive component and the polar component. So now let us say that we can combine these two, this Young's equation, by the way, this equation is called the Good-Girifalco equation. So this equation, Good-Girifalco equation, we can combine these two. So basically in essence, I write for gamma SL as gamma S minus gamma L cos theta, and then substitute over here, and if I do that, then I get this equation, gamma L into 1 plus cos theta is equal to 2 into square root of gamma S LW into gamma LW plus square root of this, and this particular equation is called the Young-Dupré equation. So Young-Dupré equation used very often, a lot in this area of literature, area of research, in which we measure the contact angle of a liquid, okay, on a solid surface, and let us say if we know the surface energy of the dispersive component and polar component of the liquid, okay, and we can then find out the gamma S LW and gamma SP, but no, that is not correct. It is like this. See, there are two unknowns here, gamma S LW and gamma SP. So actually you need two different equations. So you have two unknowns. So if you want to solve this equation, okay, for two unknowns, you actually need two equations, and therefore you need two different liquids to be placed on this solid surface, and corresponding contact angles have to be measured, and therefore you can, so basically you will have gamma L1 into 1 plus cos theta 1 is equal to 2 into square root of gamma S LW gamma L1 LW plus, let us say it is gamma SP and gamma L1 P, and let us say you have got the second liquid, that is L2 1 plus cos theta 2, this is equal to 2 into square root of, this is gamma S LW gamma L2 LW plus square root of gamma SP and gamma L2P. So you have two equations here. So you have two such equations, and you know this quantity and this quantity here, let us say we know this quantity and this quantity here, then we can solve this equation and find out the gamma SLW and gamma SP, and summation of that gives me the total value of gamma S. That is the. So, I will stop here today and I will take up this discussion further in the next lecture. Thank you.